Welcome to Chapter 1, Complex Numbers. In this topic, we will learn why complex numbers are important in engineering and technology. For example, in electrical circuit, in quantum mechanics, and also in wave motion. Complex numbers help us deal with situations where real numbers are not enough. Let's start with this quadratic equation. X squared plus 4x plus 5 equals 0. Using the quadratic formula, here a is equal to 1, b is equal to 4, and c is equal to 5. The one that I want you to focus on is this area related to what we're going to discuss in complex number. So if I were to substitute this, you'll see that you will get 4 squared minus 4 times 1 and times 5. So basically you will get 16 minus 20, which will give you negative 4. So if you write it down, you will get the square root of negative 4. If you try to input it in your calculator, you will see that you will get math error. It can't be calculated because it is not a real number. So square root of a negative value is not a real number. So Euler here discussed it and introduce a new symbol, J, or in some books they will use I, to represent a set of negative 1 to solve the problem of negative square root. And this is where complex numbers start. So J equal to square root set of negative 1 will give you J squared equal to negative 1. So again, this was obtained from J equal to square root of negative 1. Now that we have this in mind, if we try to solve this equation, okay, what do we get? So let's just rewrite it down. Negative 4 plus minus. Now, what will the square root of negative 4 become if we consider J? Let's write it down a bit. So we have J equal to the square root of negative 1. So is there any way that we can split this? Right? We can pull out the set of negative 1. Yes, the square root of negative 4, right, can also be written as square root of 4 times square root of negative 1. So if we try to solve this, we will get 2 and this will become j. So using this idea, we can write -4 plus minus 2j over 2. And if I want to simplify it down, we can get -2 plus minus j. So each root now has two parts. The real part, which is -2, and the imaginary part, with this one. This is what we call complex number. It has both real and imaginary part. According to definition 1.1, complex number is written as z equal to a plus bj. Here, a is the real number and b is the imaginary part. For example, if we have z equal to 3 plus 4j, we can say that the real part of z is 3 and the imaginary part of z is 4. Next, two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. For example, this z equal to 3 plus 4j, right, is said to be equal with another equation of 3 plus 4j. They should have the same real part and the same imaginary part. If they are having a different number and they are considered not equal. Now, let's learn how to evaluate higher powers of j. Instead of memorizing, we will use a simple rule. The simple rule that is retrieved from the idea of j equal to cert -1. So for j to the power of 1, which is this one, we are not going to change it back into the set of -1, so we are just going to retain it like this. So j to the power of 1 is equal to j. Okay, secondly, j to the power of 2, right, if we put it like this, you will get -1. Then j to the power of 3 is the -1 from j squared times with this. So we have negative 1 times j, or we can say negative j. And we have j to the power of 4, which is j squared times j squared, which is equal to negative 1 times negative 1, which is equal to 1. Let's look at the power of j, the rule of the power of j, right, in a cycle. So we have j to the power of 1, which is equal to j, and we have j to the power of 2, which is equal to negative 1. We have j to the power of 3, which is equal to negative j, and we have j to the power of 4, which is equal to 1. And after that, it doesn't matter how big is the power, it will just cycle back to j1. What does it mean by this? Let's do an example. Let's say j to the power of 23. How do we figure out what is the value of j to the power of 23? So we know that the whole cycle is 4, so we are going to just divide 23 over 4. Right, I will do long division. So 23 over 4, which will give you 5 with a remainder of 3. What does it mean here is that j23 at most will have 5 complete cycle of 4, and this 5 complete cycle is equal to 20. So we still have the remainder of 3. So we know up until the 20th, up until the 5th cycle, which is the 20, we are getting j equal to 1. So actually we can say that j20 is at this point. So how to figure out the actual j for this question? So the remainder of 3, so you should have the 21, 22, 23. So j23 should give you negative j, right? So j23 is equal to negative j. Let's try to look at another one. Let's try a bigger value of power, which is j66. So we have 66, right? 4. So if we try to solve it, we have 1, 4, remainder is 26, 6 is 24. So what we can see here is that for j26, right, it can have 16 cycle of 4, right? 16 cycle of 4. So basically this 16 cycle of 4 will give around j64, right? So we have here j64 equal to 1, right? This j64 equals to 1 with a remainder of 2. So to complete it to j66, we just need to move another 2 steps, right? Because the remainder is 2. So this is 64, 65 and 66, right? Remainder is 2. So j66 is equal to negative 1. That is how you figure it out. You can try any power, just look at the remainder. That's all. Now let's identify real and imaginary part. Let's look at example 1.2. for 15, right? If you want to write it in the standard form, we can write it as 15 plus 0j. So the real part is 15 and the imaginary part is 0. For B, it can be written as 0 minus 7j. So the real part is 0 and the imaginary part is negative 7. Alright, the same goes for this one. It is already completed, so we can just define the real value is actually negative 5 and the imaginary value is 9. And as for D, it is a little bit non-dry, right? So let's try to figure out how to do it. So we have the higher power of j here. As you can see, we have j squared and j to the power of 3. So what we are going to do first is to convert all of the j's into numbers using our j rule. So we have 4j plus our j squared is equal to negative 1, right? So negative 1 and minus 3j to the power of 3. So we have minus 3 negative j. So this will give us 4j minus 1 plus 3j. That is how you figure it out. But it can still be simplified. Remember, for one standard form of complex number, it will only have one real part and one imaginary part. So for this one, 4j, right, we can sum 4j and 3j, so you will get 7j. So we have negative 1 plus 7j. And if we are to define the real part and imaginary part, negative 1 is the real part and 7 is the imaginary part. So let's recap. We learned that complex number appear when we get the set of negative 1. We use j to represent this set of negative 1, and from this we can also get j squared equals to negative 1. And every complex number has two parts, a real part and an imaginary part, written as z equal to a plus bj. For higher powers of j, just divide the power by 4. Remember this cycle. And check the remainder. And that will give us the answer easily. Doesn't matter how big is the power. Okay, so next we will learn on how to add, subtract, and multiply complex numbers. Thank you and see you in the next lesson.